welcome to the next lecture on the modeling and analysis of electrical machines. What we had started doing in the last lecture was try and develop the steady state models of electrical machines. The DC machine of course was a simple model which we did at the time of deriving the dynamic equations of the DC machine. The induction machine and the synchronous machine, we have developed equations based on a totally different idea or a totally different approach as compared to the machine representations which one would have derived in a first course on electrical machines. And these equations apparently do not look like anything which is like what one would have done in the first course on electrical machines, and therefore we wanted to find out how these equations or these models look like under steady state operations. And therefore we tried to reduce these equations to more simpler forms under steady state, and then we wanted to see whether the conventional known equivalent circuits of machines that one has studied, for example the induction machine equivalent circuit, whether it can be derived from these equations, and if so, is it exactly the same as what one would have done in the earlier course on electrical machines, or is there any difference. So those are the things that we wanted to investigate, and we started looking at the induction machine equations. So let us look at that once again. We just started that in the last lecture, so let us see those equations again. So steady state analysis, and we are looking at induction machine. So in the steady state representation, what we are looking at is a per phase representation. That is what one would look at as an equivalent electrical circuit, and to arrive at that we have these two equations. Vds is equal to Rs plus Ls P into Ids minus omega s Ls Iqs minus Lm P Idr minus Lm plus Lm P Idr minus Lm omega s into Iqr, and we are looking at steady state, and therefore d by dt terms can be made 0. Why is it that d by dt terms can be made 0? These equations are written in the synchronous reference frame, and in the synchronous reference frame we have already seen that all the variables reduce to DC terms. An excitation, an AC voltage that is applied to the stator at 50 hertz, say, in the synchronous frame looks like a DC term, and therefore if one were to do a differentiation operation on a DC term, the result is 0, and therefore this term goes to 0, and similarly this term goes to 0, and therefore under steady state what you get is Rs Ids minus omega s Ls into Iqs minus Lm omega s into Iqr. This is Vds, and similarly Vqs would give us Rs Iqs plus omega s Ls into Ids plus omega s Lm into Idr. So these are the two expressions for the stator voltages. Similarly, you will have two expressions for the rotor voltages, that is VDR equals RR into IDR. Again, d by dt terms can be neglected because we are in the synchronous reference frame. So RR into IDR plus, or rather minus, Lm omega s minus omega r into IQS minus Lr omega s minus omega r into IQR, and similarly VQR is RR into IQR plus Lm into omega s minus omega r into IDS plus Lr into omega s minus omega r into dr. So these are the equations for the rotor voltages under steady state. And what we want to do, since we are looking at the per phase equivalent circuit in the natural reference frame, in the 3-phase reference frame, we need to transform these equations to the normal phase voltage of A phase stator and the phase voltage of the rotor. And we know that we have gone to the dq equations, Vd, Vq and V0. This was obtained as cos theta and sin theta minus sin theta cos theta and root 2 by 3 times 1 minus half 0 root 3 by 2 minus root 3 by 2 1 by root 2 1 by root 2 and 1 by root 2 times VA, VB and VC. So this is the transformation that takes us from the ABC reference frame all the way to dq, and what we want to do is exactly the inverse. Now we want to go from the dq equations that are there back to ABC, so that we can find out what VA is in terms of all these terms that we have represented. Similarly, what IA is in terms of all these terms that have been represented. So if you want to do the inverse, what you do is Vd, Vq and V0 pre-multiply by the inverse of this matrix, that is cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. So this matrix and this matrix are nothing but the transpose of each other. Similarly, you multiply again by the transpose of this matrix, which is 1 0 1 over root 2 0 minus half root 3 by 2 1 over root 2 and minus half minus root 3 by 2 1 over root 2. The scalar remains the same, so that is still root 2 by 3. So you get VA, VB and VC, and what we are interested in is only VA, and therefore these two terms we are not interested in. because we need to develop a per phase equivalent circuit, and therefore we only look for the expression for VA, and VA is nothing but root 2 by 3 times 1 over root 2 multiplied by this one, and therefore we can reduce that VA is root of 2 by 3 times. The first term alone is going to be of importance, the second term in this is multiplied by 0, and third term is going to come here, and this term is going to be 0 because V naught is 0. So, this reduces to Vd cos theta minus Vq into sin theta, and by the same token what you would have is Ia equals root of 2 by 3 times Id cos theta minus Iq sin theta, and further we are looking at the synchronous reference frame, and therefore theta equals omega synchronous into time. So, what we need to do is now substitute these expressions for Vd and Vq into what we have got. When we say Va, we have not really specified whether it is Va of the stator or Va of the rotor. It could be either one depending upon what you substitute here. If you make this as Vds, that is pick up the expression from here, and then Vqs, then what you get is A phase voltage of the stator. If you substitute these two equations, what you get is A phase voltage of the rotor. So, let us substitute that, and what we get is Va equals root of 2 by 3 into this expression multiplied by cos theta. So, that is Rs into Ids cos theta minus omega s Ls into Iqs cos theta minus Lm omega s Iqr cos theta, and then plus Rs it is minus Vq sin theta. So, this is minus Rs Iqs sin theta minus omega s Ls Ids sin theta minus omega s Lm Idr sin theta. So, that is the expression we have, which can then be simplified as root 2 by 3 into Rs into, we combine these two terms. So, that is Ids cos theta minus Iqs sin theta, and then we combine these two terms omega s Ls terms. So, that is minus omega s Ls into Ids sin theta plus Iqs cos theta, and then minus omega s Lm into Iqr cos theta plus Idr sin theta. This is what one gets if we multiply these two terms. Now, what you see here is Ids cos theta minus Iqs sin theta, and that is exactly what we have here. Ia is Id cos theta minus Iq sin theta, and that root 2 by 3 factor is here, and this refers to ds and qs, and therefore we can write this as Ias. So, this term becomes Rs into Ias. When you come here, what you have is Ids sin theta plus Iqs cos theta. So, imagine you were to differentiate this term with respect to angle, considering, or with respect to t, considering the fact that theta is given by omega s into t. So if you differentiate this, what you would get is root of 2 by 3 into minus id sin theta, differential of cos is minus sin, and then minus iq cos theta, and theta is omega s into time. So d theta by dt, which is multiplied by omega s. So that is exactly what you have here, minus omega s into id sin theta plus iq cos theta. So this term is nothing but plus ls into d by dt of ias. So that includes the root 2 by 3 factor as well. And then we look at this term. So again you have iqr cos theta plus idr sin theta, negative sign taken out, but now that this is idr and iqr, this term will give us iar and diar by dt. So this is nothing but plus omega s into lm diar by dt. So this whole long expression can be compressed into these three terms. VA is RS IAS plus LS into d by dt of IAS plus this. So therefore let us write that down, RS into IAS plus LS into d by dt of IAS plus this omega s comes out as a result of multiplying this. So we do not write that explicitly, Lm into diar by dt. So that is what you get. So now let us look at the rotor voltage. VAR is again nothing but root of 2 by 3 times VDR into cos theta minus VQR into sin theta, which can be taken up from these two expressions. And if we look at these two expressions, what we find is that instead of omega s you have omega s minus omega r here, instead of omega s again you have omega s minus omega r. Therefore fundamentally these two equations look pretty much the same, except for the fact that instead of omega s you now have omega s minus omega r, and therefore one could, anyway let us write that down. So VDR is RR into IDR cos theta minus Lm into omega s minus omega r into I QS cos theta minus LR into omega s minus omega r into IQR cos theta plus minus RR into IQR sin theta, and then plus Lm into omega s minus omega r into IDS. It's not plus here, it is minus because you are subtracting, and then one more minus term, LR into omega s minus omega r IDR into sin theta. So this is what you will end up with, and that can be written therefore as RR into IAR. These two terms together would give us IAR, and then this term give Lm into omega s minus omega r into IQS cos theta plus IDS sin theta, and then minus Lr into omega s minus omega r into IQR cos theta plus IDR sin theta. So, what we have is this expression, which one can write now as RR into IAR minus Lm. Now, this term omega s minus omega r, omega s is the synchronous frequency, omega r is the rotor speed, and in the case of induction machines, the ratio omega s minus omega r by omega s is written as the slip s, and therefore omega s minus omega r can be written as s times omega s, and therefore this is s times omega s multiplied by this expression, and then you have minus Lr into s times omega s multiplied by the second expression. And we know what is occurring inside these two is nothing but the derivative of I, and therefore we can write this as RR into IAR minus Lm multiplied by s. What we get here is IQS and IDS, and therefore it is the derivative of the stator current, that is A phase stator current. Omega s comes as a result of differentiation that we have seen already, and therefore this is nothing but plus d by dt of IAS, and here what you get is the derivative of the rotor current, and therefore this is nothing but plus Lr into s into d by dt of IAR. So, these are the two expressions that we will end up with. So, what we will now do is convert to the phasor notation to make it easier to handle. So, the first equation is the equation for the stator voltage VAS. So, VAS as a phasor is then equal to RS into IAS, where I is a phasor, and now you want to represent this one Ls d by dt of IAS. So, in phasor notation that then becomes plus j times omega Ls into IAS, and j times omega omega times Ls is nothing but XS, that is the stator impedance, inductive impedance, and then you have plus j times XM into IAR. So, this equation in phasor form has now been written. Similarly, you have VAR is equal to RR into IAR plus S times Lm. Now, dIAS by dt into Lm can now be represented as j times Xm IAS phasor plus j times XR multiplied by the slip into IAR phasor. Now you may have a doubt that comes up at this instant. Now we are looking at doing a differentiation of IAR, and the rotor current in reality is not at the frequency of the supply, but it is at the frequency of slip. So one may ask why slip frequency is not coming. So that in fact is indicated by S here, but equation wise what you are differentiating is this expression IQR cos theta and IDR sin theta, and theta is nothing but omega s into t, and therefore when you differentiate what you will get is only the supply frequency. This s comes as a result of this omega s minus omega r, and therefore when you look at it here what you get is XR, and that is the stator current phasor. Now the rotor in the induction machine is invariably shorted, and therefore VAR is 0, and therefore that is what it is. So now what we can do is manipulate these two equations. What we will do is we will add to this JXM into IAS and subtract JXM into IAS. So that makes no difference as far as the equation is concerned, and similarly here what we will do is divide this expression by S, and therefore this S goes away, this S goes away, and what you get is RR by S into all those terms. And now what we will do to this expression is add and subtract XM into IAR and minus XM into IAR. So with the result, the first equation VAS now becomes RS into IAS plus these two terms can be combined, and the self inductance or the self reactance minus the XM value will give the leakage inductance or the leakage inductive impedance of that. So this is nothing but J times XL into IAS plus J times XM into IAR plus IAS, and in the second term 0 is equal to RR by S into IAR plus, similarly here if you look at these two terms, XR minus XM would be the leakage inductance, and therefore J times XL into IAR. XL is, this is XLS, this is XLR, leakage inductance of the rotor. Again remember, we are at the outset when we started with the synchronous reference frame machine equations, we had already referred everything to the stator, and therefore all these terms are stator turns referred entities. RR for example is RR, that is the rotor resistance referred by number of turns to the stator turns, therefore it is really RR dash in the conventional sense. And then you have these two terms, so that is J times XM into IAS plus IAR. So this is what you get, and this can be represented as a simple equivalent circuit in this manner. So, let us say you are applying VAS here, that VAS is consumed as a stator resistance term, the current flowing in is IAS. So, that is consumed as a stator resistance term, and then you have a leakage inductance, this is RS XLS, and then you have an XM through which both IAS and IAR are going to flow. So, if I now represent this by an inductance here, and this current is IAS, this current is IAR, then these two together flow in this inductance, and if you now apply KVL around this loop, so this is IAR. So, if you now apply KVL around this loop, you precisely get this equation. Now, to focus on the second side, you have the rotor voltage VAR, which is 0 alright, but the rotor voltage is then consumed as RR by S multiplied by IAR, and then a leakage inductance XLR. And now if you write KVL around this loop, IAR is already flowing here, therefore this voltage is equal to resistive drop plus the inductive drop plus this voltage, which is nothing but XM into IAS plus IAR, and the rotor is usually short circuited, and therefore VAR is 0. So, that is the equivalent circuit which one gets on a per phase basis for the induction machine, which definitely looks very similar to what we have studied in the first course on machines, except for this additional resistance which comes in the normal exact equivalent circuit of the induction machine. Where is this resistance? Why is this resistance not there in the formulation that we have done? This resistance is not there because all this analysis neglects core losses. Since we have not considered the effect of core losses in this development, it is not represented in the formulation that we have done, it does not come out in the equivalent circuit also. So, if we neglect core losses, whatever we have done, we have derived as the induction machine equivalent circuit is still applicable in comparison with what we had studied earlier in machines first course on machine. So, from this then one can go about to predict all the machine behavior under steady state, one can derive the speed torque relationships and then the various approaches to speed control one might have, and then solve, I mean if you are going to connect this induction machine to a big electrical network, one can then solve it as an equivalent electrical network to find out how the machine is going to behave at a particular slip. Now, the derivation must have also made it very explicit that this equivalent circuit is valid only under sinusoidal steady state. This is important, that is what we started out with right at the beginning of the course, that the conventional equivalent circuits that one have studied are valid only under steady state, and that too sinusoidal steady state. This derivation makes it very evident that it is indeed so. You cannot use this equivalent circuit, for example, to find out how speed is going to change if you give a supply voltage here. If all of a sudden you switch on an AC voltage here, how is speed going to change? This equivalent circuit does not predict. You have to make use of all the elaborate DQ formulation equations that we have derived and combine it with the mechanical equations of the machine in order to find out how the system is going to behave. Sometime later on in one of the lectures we will see a response, a solution of these equations done through a computer to see what kind of responses one gets when machine undergoes an acceleration or a deceleration, but that is for a later date. And for now we have achieved our job of deducing the steady state equivalent circuit from this representation. This is for an induction machine, a 3-phase induction machine. So how does this work for the synchronous machine? Let us now look at steady state representation or the model for a synchronous machine. Let us get rid of this also. In the case of synchronous machine, let us write down the equations first on the d and q axis. So now we move on to synchronous machines steady state analysis, and we are going to look at synchronous machines, and in that we are going to look at salient pole machines. As we saw earlier, the cylindrical rotor variety is easily deduced from the salient pole equations by setting the direct axis synchronous inductance equal to that of the q axis synchronous inductance. So it is enough if we solve this, the other case is easily done. So we have again the equations on the d and q axis. Vds is nothing but Rs into Ids, and then plus Lds into Pids plus Lmd into Pif dash minus Lqs into omega s into Iqs. So this is as far as the stator d axis is concerned, and Vqs is Rs into Iqs plus Lqs into Piqs plus Lds into omega s Ids plus Lmd into omega s into If dash. So these are the two equations we get for the stator of the synchronous machine. Now in the case of synchronous machines, we have, apart from these two, we have the field equation as well, which is the rotor expression, and the rotor expression is not going to give us major information because the rotor is not really connected to the AC circuit. The rotor is fed from the DC side, and under steady state when we are looking at it, it is going to carry a steady field excitation, so which is not normally considered therefore in the steady state analysis. In fact, if you look back at your earlier electrical machines exposure, you would not have discussed anything with respect to the field other than saying the field induces an EMF in the stator. So here also therefore in steady state analysis there is nothing to consider in the field, so we leave that out. Now again we are looking at steady state, and the synchronous machine equations are already in the synchronous reference frame, and in the synchronous reference frame, as we had noted earlier in the case of induction machines, all terms are DC terms, and therefore derivatives goes to 0, and therefore this term goes to 0, this term goes to 0, this goes to 0. So these are all the terms that go to 0. So Vds is nothing but Rs Ids minus Lqs omega s into Iqs, and Vqs is given by these 3 terms. Now what we want to get the A phase voltage, and how to get the A phase voltage? We proceed with the same route. If you want A phase voltage, it is root 2 by 3 times all this, and therefore Vas is nothing but root of 2 by 3 times this into cos theta. So Rs Ids cos theta minus Lqs omega s Iqs cos theta, that is Vds cos theta, and then you have to do minus Vq sin theta. So minus Rs Iqs sin theta, and then minus Lds omega s Ids sin theta minus Lmd omega s If dash sin theta. Now again note that theta is equal to omega s into t, since the reference frame is synchronous reference frame. And now you have an Rs term here and an Rs term here, and this is Ids cos theta minus Iqs sin theta multiplied by root 2 by 3. So you have Rs into Ias, if you take that out, plus root of 2 by 3 times this term minus Lqs omega s into Iqs cos theta minus Lds omega s into Ids sin theta minus Lmd omega s into If dash sin theta. This is what we have. Now we know that Ias is root of 2 by 3 into Id cos theta, that is already written there. Well, okay. So Id cos theta minus Iq sin theta. So having written it in this form, what we can see is theta is nothing but omega s into time. So you are obtaining Ias as an addition of some term depending on cos theta, cos omega t, and another term depending on sin omega t, which means the resultant, if you add cos omega t term and sin omega t term in some ratio, the resultant will be another sine wave which is phase shifted with some phase shift, but at the same omega s as well. And we know that if you are going to write a sine waveform, for example some flow of current I, and it is some, let us say, cos of omega t, the term that you put here will represent the amplitude of the sine wave. And if you want to get at the RMS, since it is a sinusoidal waveform, you take the amplitude and divide it by root 2, and therefore if you want the RMS of this waveform, what you have to do is you have to take the amplitude and divide by root 2, and root 2 is already there. So if you divide by root 2, this goes away, and then you will just have 1 over root 3. Okay. Now it is necessary to, before we go ahead, remember or try to recollect what is the phasor notation, right. So let us briefly look at the phasor notation before we move ahead. Now if you have some variable V, let us say, is equal to Vm cos omega t, and you want to represent this as a phasor, what do you do? This is considered to be a phasor. A phasor is nothing but an arrow which is drawn in the complex plane. So this is your real axis and this is the imaginary axis. So that is the plane that we are talking about. The phasor is nothing but an arrow represented in the complex plane, and that arrow is assumed to rotate at the angular frequency that is mentioned here, omega. So we can draw, let's, in general it's given as omega t plus phi. So now you can draw an arrow which is displaced from this axis by an angle of phi that is mentioned here. The length of the arrow is normally taken to be the RMS value of the sine waveform, of the sinusoidal waveform. So the length of the arrow is Vm by root 2, that is this length, right. So if this is the representation of Vm cos omega t plus phi, let us say now you want to represent a term V1 which is Vm cos omega t. The phasor for this will then, because phi equal to 0, the phasor length will be Vm by root 2 and it will lie entirely on this axis. So this is V1 phasor. Okay. Suppose you have another V2 and V2 is given by Vm into sin omega t. Where will this phasor be? So this can be written as Vm into cos of 90 degrees plus omega t, but cos of 90 plus omega t will give you minus of sin theta, but what we want is plus sin theta. So you put another minus sign here to get plus sin theta, and if one does that, what you see here is you have Vm cos 90 plus omega t. So cos of omega t itself would be located along the horizontal here, and therefore cos of 90 plus omega t would have been located here, but then you have minus of cos 90 plus omega t, and therefore V2 phasor would really lie here. This is your V2 phasor. So if you now have minus Vm sin omega t, if we now have minus Vm sin omega t, then that phasor would be represented as, since Vm sin omega t is below, minus Vm sin omega t will then be here, and therefore minus Vm cos omega t will then be a phasor lying along the other direction. So it is important to understand or recollect this, because what we are going to be dealing with is these kind of phasors. So this term IAS equal to root 2 by 3 sin omega into ID cos theta minus IQ sin theta can now be converted into a representation as phasors, because theta is nothing but omega t and this is also omega t, and that is going to come in useful in simplifying this equation further into the phasor notation, because as far as synchronous machines are concerned, one does not really make use of an equivalent circuit in the steady state analysis. Rather what one looks at is the phasor representations in the steady state analysis, so that one can solve whatever electrical network that is going to be connected, one can understand how it behaves. So to get to that phasor we briefly recollected how the phasor representation is. We will make use of that and develop the phasor notation for the salient pole synchronous machine in the next lecture. We will stop here for today.